Welcome back, AP Statistics. This is Chapter 11, Sample Surveys. We're going to be talking about the science and perhaps the art of proper sampling. So, ideally, when studying a population, we would like to know about every member of it. Every possible subject that we could study relevant to our study comprises the population. We'd like to know a bit about everyone. However, we seldom have the capabilities to do so. That is why most of what we call statistics even exists. We cannot study the whole population, so we have to get a bit creative. Instead, we can collect a sample of the population. A sample of the population is kind of like a sample of soup. I cannot lay claim to this analogy. This is the book's analogy. I'm not sure if it originated with them. Maybe it did, maybe it didn't. But it is a brilliant analogy, and I'm going to be using it a lot because I really like it. So a sample of the population is kind of like a sample of soup. If you take a spoonful of soup, it probably tastes like the rest of the soup, unless, of course, the spoonful does not contain all the ingredients. So getting a sample that contains all the ingredients of the population, as it were, requires a rigorous approach. You'll find that it doesn't matter how big the population is. You can have a very, very small sample relative to the population, and you can get a really good idea of the contents of the population. The trick is to get a sample that does a good job representing the population. And that's why we need to talk about bias. When sampling technique favors gathering data from some members of a population more than others, we say the sample is biased. Now, it would be a misconception to say that biased sampling is intentional. Quite the opposite. Unless you are very intentional in your approach, your sample will be biased. And to an extent, it is impossible to avoid bias in some cases. Surveys can show preference to some or others, whether intentional or unintentional, and we're going to be talking about the unintentional ones mostly. For example, younger generations may be more willing to take internet surveys, and internet surveys are notoriously unreliable, while older generations might be more reliable to take mail-in surveys, which tend to be more reliable, but it's harder to get people to do them. The homeless population as well as the ultra-wealthy are often overlooked for mail surveys. The former may be underrepresented for online surveys too. So the homeless population, they're notoriously hard to get a hold of, and the ultra-wealthy, well, they travel too much, so it's hard to get a hold of them too. The only way to ensure bias doesn't play a role in sampling is by ensuring that subjects are chosen randomly. We call this randomizing. So, to the soup analogy, stirring the pot of soup is like randomizing. Even if an ingredient were added that you didn't know about, if you stirred the pot of soup, you would disperse the unknown ingredient evenly. That's what's so awesome about randomizing, which we'll spend a good amount of time talking about. We are protected from bias if our sample is truly random, even if there is an element of our sample we haven't even considered. That's power. One way to tell a population has been in fact randomized is when multiple samples are similar across several variables. If we have multiple similar samples, that very, very likely means that we've collected samples that are representative of the population too. Here is an example of such samples. Here are summary statistics comparing two samples of 8,000 drawn at random from a company's database of 3.5 million customers. So we have these two samples right here, and a whole bunch of variables are considered. And we look at the numbers comparing the two samples, and they look awful similar across the board. So do we think these samples are not only similar to each other, but representative of the population of the company's customers? Well, I think so. Here's the book's answer. The two samples look very similar with respect to these 7 variables. It appears that randomizing has automatically matched them pretty closely, so we've taken some good samples, or at least our textbook writers have. We can reasonably assume that because the two samples don't differ too much from each other, they don't differ much from the rest of the population either. Now let's talk about the size of the sample. And this is a counterintuitive fact of sampling that I guarantee the AP test is going to try to get you on. Interestingly, the proportion of the population in a sample is not as important as the size of the sample. That is counterintuitive. For example, a survey of 100 randomly selected students tells us as much about a student body as 100 randomly selected voters tells us about the country. Now you may be thinking to yourself, Mr. DeClerico, even at a large university, the size of the student body is nothing compared to the size of the country in terms of the population. Well, it doesn't matter. A survey of 100 randomly selected students does just as good a job as 100 randomly selected voters, regardless of the size of the populations we are studying. Back to that soup analogy, a spoonful of well-stirred soup tells us as much about a flavor of a bowl of soup as it does about a pot of soup. And this is what makes the soup analogy so great. It captures this concept that it doesn't matter how big your population is, it just matters how big the size of the sample is, regardless of the population. What matters is that the soup is stirred, there's randomization at work, and that the spoonful contains enough soup to get all the flavors, that's sample size at work. How big is an appropriate sample? Well, it depends. It depends. What an annoying answer. But it depends on the study. And we will discuss this as the year goes on. Depending on what we are doing, sometimes a small sample is A-OK, sometimes a small sample is trash. And so we will determine what an appropriate sample size is as we go. So some of you may be thinking, Mr. DeClerico, why can't we just take a census? Why can't we just crack our knuckles and do the good long work of finding information about the entire population? Why can't we just do that? Why do we need to go through all this guesswork and sampling? And let's just take a census, all right? Well, a sample of the entire population is called a census, and there are some instances in which a census is appropriate, but generally in statistics, a census is about as close as you can get to a dirty word. If the entire population is easily accessible, there's no reason why not to take a census. If I wanted to learn some information, perhaps, about Faith Christian Academy, some aspect of the student population, say a proportion of students who order lunch on Thursday as opposed to packing their own from home. I could very easily just go to all 3 lunch hours, see how many students are at lunch, and see how many students go through the lunch line and swipe their cards and all that. And I could very easily determine the proportion, if I were to do this over the course of a couple of Thursdays or every Thursday over the course of a year, I could determine with almost perfect accuracy, going from year to year, what a Thursday lunch would look like in terms of student buyers versus student lunch from home packers. Okay? I could totally do that, but that's because Faith Christian Academy does not have a massive population. However, though counterintuitive, sampling can often produce better results than a census. Now, if you thought that this lesson is already counterintuitive, you just buckle your seatbelts. A census is expensive. Duh. If we want to learn about a very large population and we are intent on studying absolutely everyone, it's going to cost a lot of money. Reaching people, especially those hard to reach people like the homeless and the ultra wealthy and folks who are notoriously hard to reach, that takes a lot of effort. Effort takes coordination among a group of researchers, and that takes money because that's going to take time. Time is money. And since there are a lot of subjects to locate, That's going to take a lot of time, a lot of money. Things really blow up pretty fast. So populations rarely stand still, all right, especially in the U.S. If you're studying folks in the U.S., people move a lot, if you haven't noticed. Some subjects arrive, some subjects leave, and unfortunately, if we're talking about people, some subjects that you're studying, if you're studying the entire population of a country, some subjects pass away, and also some subjects are born, all right? So the population studied in the beginning will likely not be the population that's being studied by the end. It's easy also to double count in a census. U.S. Census has a really big problem counting college students. This is a continuous issue. Well, why is that? Well, their names correspond with multiple addresses. They have a campus address where they get their campus mail, and they also have an address at home. How do you tabulate the number of people? Well, one way to figure that out is to see the number of addresses and the number of people per household. Well, college students have multiple addresses. That can become a problem when tabulating the number of people in a large country like the United States. So now we need to talk a bit about statistics, because that's how we study samples. We gather information about a sample, those are called statistics, and we use statistics to estimate parameters, which are details about the population. In the practice of statistics, a model used to represent a population consists of a few key numbers called parameters. A few that we've already discussed are the population mean, which we denote with the Greek letter mu, and the population standard deviation, which we abbreviate with this lowercase sigma. When discussing a sample, when summarizing a sample that is, we also use a few key numbers, and those are called statistics. A few that we discussed are x bar, y bar, etc., the sample mean, and those are literally just x or y, which is a random variable, with a little bar on top. You've seen it before if you've been paying attention in videos past. So those fellas are, speaking of notorious things, they're notoriously difficult to type in Google Slides, which I'm using here. So I'm just going to put some little quotes around X bar and Y bar. Just bear with me there. So that's the sample mean. That, of course, corresponds with the population mean. By learning about the mean of a well-gathered sample, you can learn a bit about the mean of the population. And S, the sample standard deviation, of course, corresponds with sigma, the population standard deviation. So if we have a good sample, we can take the sample standard deviation and learn a bit about the population standard deviation. We want to pick a sample that resembles the characteristic of the population, and such a sample is said to be representative of the population. That is the term that you will see throughout the year. Is the sample representative of the population? Here are a few more parameters and statistics. This is one that we will probably not see, though I have taught a statistics course, and still do, that features this one right here. This is, looks like a letter P, but it's actually a Greek lowercase letter rho, which would make an R sound, incidentally. Go figure. And the sample statistic is R, which you definitely will see. And have seen. R is the correlation coefficient for a sample. This is the corresponding population correlation coefficient. This is, we fit a regression line to a sample, and R is the slope of the standardized data. If we were to do the same thing with an entire population, that would be rho. So the intercept of a linear model, we have b sub 0, and in your formula sheet it's just called a, but the textbook, and I personally prefer to use b sub 0. For the population, that's going to be beta sub 0. All right, that's a Greek lowercase beta, which interestingly it looks like a capital B. So it's beta 0 or beta naught, you will sometimes hear it called. So the again, like R and rho, we have a sample statistic, which corresponds to a population parameter. If we were to consider all possible data values we could study, the intercept of the linear model would be this Greek letter beta sub 0 or beta naught. Similarly, the slope of a linear model, B1, B sub 1, or just B if you're looking at the formula sheet for this class that you'll have on the AP test, that corresponds with a beta sub 1. And also for proportions, you have for the population P, which does look a lot like rho, but you won't be really seeing rho this year other than on this slide. So if you see a figure like this, it's P. And P is the parameter for a proportion. A proportion is a part-to-whole analysis, all right? Usually represented as a fraction, sometimes represented as a decimal as well, all right? So a proportion for the entire population is P, and if we're just looking at a sample and doing a little part-to-whole analysis, we would say P hat, all right? P hat, just like we put a hat over the response variable in linear regression that we are trying to predict values of, a guess at P would be the same letter P, but with this little estimate indicator, the little hat. Here are some questions to get you thinking about the content we've discussed thus far in Chapter 11. So, various claims are often made for surveys. Why is each of the following claims not correct? So let's look at letter A. After I'm done reading letter A, I'll give you some time to think about it, and then I'll reveal the answer. Letter A. It is always better to take a census than to draw a sample. What do you think about that statement? Think about it, and then unpause the video when you've given it some thought. All right. Well, let's assume that we're ready to go on and say that, yeah, censuses are generally not good. Taking a census is usually impossible, and even if it is possible, it's expensive and time-consuming. Unless data about the population are readily available, a large sample that's representative of the population will do. So let's look at letter B now. B is kind of a sneaky question unless you make an assumption that I have indicated down here. When I first saw this question, I was actually a bit confused, and then I realized that I needed to assume this to make this question make a bit more sense. Stopping students on their way out the cafeteria is a good way to sample if we want to know about the quality of food in the cafeteria, right? Now, that seems like a good idea. You stand outside the cafeteria at the risk of being very annoying, and you ask students about the quality of food there, and you get their responses, and you get an idea of how the food is at that cafeteria. But we're going to assume something. We're going to assume that in this context of a college campus, the sample could be biased if there are other places to eat on campus. Assume that this cafeteria is not the only place to grab a bite to eat on campus. Why would this be a bad model of survey? Take a moment, think about it, and then I'll reveal the answer. Okay, I'll assume we're ready to continue. Students who are leaving this cafeteria may prefer eating at the cafeteria as opposed to other places on campus, like perhaps a student union or maybe a restaurant in town if they have a little cash from an on or off campus job, or from home. So this looks like a decent idea for a survey, but if you're considering there are other places to eat, there may be a reason why people have chosen to eat here. You've sampled people that seem to like this cafeteria enough, you're not going to get information about the people who would prefer to eat elsewhere, and their information is very valuable. Their information is probably a bit more negative about the cafeteria, but they are part of the population. They are part of the college community. Their opinion does matter if you want the reality of the situation. Let's look at letter C now. We drew a sample of 100 from 3,000 students in a school. To get that same level of precision for a town of 30,000 residents, we'd need a sample of 1,000. There's something fishy about that statement. It seems intuitive, but as we've seen in this section, sampling can be a bit counterintuitive. Take a minute to think, and then try this one on your own and see how you do. All right, I'll assume we're ready to continue. The proportion of the population sampled is not as important as the size of the sample. A representative sample of 100 works just as well for a population of 3,000 as it would for a population of 30,000. Using the soup analogy, it doesn't matter how big the container of soup is. It could be a stock pot, it could be a little bowl. Doesn't matter. What matters is the size of the spoonful, and that the spoonful contains a little bit of all the ingredients. That's what we're going for here. So a sample of size 100, which in a lot of cases is quite a good sample, the sample of 100 works just as well for a population of 3,000 as it would for a population of 30,000. Interestingly, and this might take a lot of thought, but something to consider, a sample of 100 might actually be bad. It might actually be too big if your population is, say, less than 1,000 people. We're going to learn about that later, that sometimes a sample can be too big, that it actually starts causing a problem. All right, let's look at letter D. A poll taken at a statistics support website, kind of like this YouTube channel, garnered 12,357 responses. Oh, if my channel could only have that many responses. Maybe by the time you're seeing this video, it will. I doubt it, though. The majority said that they enjoy doing statistics homework, bless them. With a sample size that large, we can be pretty sure that most statistics students feel this way too. There's a lot with part D that is not right. It's wishful thinking. It really is. What's wrong with part D, as much as I personally would like it to be true? Think about it and unpause the video when you're done. All right, let's look at this answer. Students who are nerdy enough to go on a stats support website are probably biased in favor of doing stats homework. We cannot be pretty sure that most statistics students feel this way too. A lot of students taking a statistics course are not math nerds. They're taking statistics because they have to for degrees that are largely unrelated to a statistics class, or they just need an elective in high school. All right? We cannot make that assumption. People who are going on the statistics support website, if they want to put that much effort into it, are either nerds at everything or just really like statistics. So that is a very biased sample. Let's look at letter E. The true percentage of all stats students who enjoy their homework is called the population statistic. What is wrong with that? I'll give you a hint. It has to do with the last two words that are appropriately put in fear quotes. Think about it, and we'll check the answer in just a moment. All right, let's see it. Well, there's no such thing as a population statistic. The correct term is population parameter.